Hello, hello,
Hi.
bro. Can you hear me?
Yeah, I can hear you.
Okay. So you have questions regarding
Yeah.
AA? Okay.
So has the next assignment been started, first of all?
Uh, the next one that you sent,
Yeah.
uh, basically, I just saw it like right now because
Oh,
WhatsApp is having issues. We are not able to send or receive the files.
I
Okay.
mean, I sent him, but I sent him like 2 days ago. No?
Uh, I got it yesterday, I think, I guess. And
Okay.
when I try to download WhatsApp is not
But
downloading the file.
yeah, but I sent it over Gmail as well as over email to Ram.
I did not get the email from you.
I sent it to him, to Ram. I sent it to the email he sent me.
Okay. Okay, when is it due?
Huh? I have, I have 5 days now.
Okay. So we have to finish this in 5 days. Okay.
It's kind of a
Sure, sure.
culmination. It's like a
Yeah,
combination of some of the other previous ones. So it shouldn't be too much more difficult in the sense that um
yeah,
it uses like the same like assignment 5 and all that. Like it uses the keypad and then the um spy and some maybe some UART stuff and did the
yeah,
digital analog converter.
yeah. Basically, this is the combination of previous one and plus new addition as well. We need to embed a timer interrupt in that to generate the different
Yeah. But there was like
waveforms.
a basic like there was a timer assignment as well, and then there was this as well. Like there was a timer, you know how there was like separate assignments with like timer, UART, spy.
Yeah,
This is just like combining those in a different application. That makes sense.
yeah.
Yeah.
Okay.
Oh my, yeah. So I sent this. I mean, it's been about a day and a half. I think I sent it like a day and a half ago. So I just like I don't want there to be delays. You know what I mean? Like if I send it to him and then he takes a day to send it to you and then you take a day to look at it, it just like
Okay, so you need to work on the hardware as well. Okay,
okay.
because it needs a lot of hardware. Okay, at least you need to have nuclear board with the DAC. Okay, and you need to have a multimeter as well. Try to get a cheapest multimeter. Okay, so we can at least measure the DC voltage while you at home.
Okay.
Okay, you don't need to go lab, but obviously to observe all these signals you will
Will
need
you be able to
oscilloscope.
okay, so I can get like I can would you be able to start working on the code itself like early on? Because I can get access to that the IC and the multimeter in like 4 days.
Okay, so basically first we need to test the spy communication because last time we did not like confirm it's working. Okay,
Oh, I see.
so sometimes the issues can come, so at
Sure, sure,
least
sure.
first we make sure that spy is working fine with the DACIC. Okay, and it is giving the correct voltage that we
Do you
want to
have that
achieve on.
IC or no?
No, I don't have that IC.
Oh man. Okay. Because
So
it's
you
like a
need to
weird time. It's like a weird time between right now, so it's like I'm unable to access it
okay, so when can you get it?
in 4 days.
Oh, in 4 days.
Is that bad? Like, will that is that something that has to be done first? Is my question.
Basically, the assignment A4, we need to check the spy communication with the IC itself. So at least when we are confirmed that the communication between the nuclear board and IC is established, then after we can like generate waveforms with the help of IC.
Right. Okay. But what I'm asking is, if possible, what I'm asking is like, would you be able to uh like work on the other parts of that code first, and then we can test the
Yeah,
communication?
yeah,
Like,
I will work on everything.
okay.
Can you open this new assignment on your, so there is one very important stuff, very important thing.
Sure, sure, sure. Give me one sec.
Yeah, for that we need IC itself.
You want me to like open? Okay, let me see.
Okay, give me the access. I can show you what things. Okay, so it's like we need to make a function generator using microcontroller. Okay, and we will use the external DAC. Okay, to generate analog waveform, spy communication. Okay, so blah blah blah. So this is the most important thing, timing
Yeah.
calculation. Okay, so we need to determine the maximum resolution possible with the DAC. For that, we need to have the IC. Okay, so yeah, so basically, we want to create waveforms, right? So waveforms created are created like this. If I can you bring the paint to
Oh,
the
sorry.
screen?
Yeah.
Okay, so if I remove all of that,
Yeah,
or
you
I
can get
can,
rid of this. It's fine.
okay, okay, so waveform are created like this. So we send one pulse, one sample, and after some millisecond, another sample, another sample, another sample, another
Okay.
sample, another sample, another sample. Okay, you see?
And that's how it
So
generates the waveform, like a sine waveform or something.
waveform. So
Yeah.
that's how we, let's suppose we want to send 100 samples in one period. Okay. So if you join this,
Samples in one Oh, okay, okay. Also, based on
okay,
the DAC and the communication, that's how you figure out how many samples per second to send.
yeah, yeah. Okay. So resolution is what maximum samples you can send without disturbing the whole waveform. What maximum number? Because if you send like 50 samples, okay, so the waveform will be like this. It will have jumps. Okay, okay, like this. So you getting my point? The more samples you cover in one period, the more smooth waveform will be, right? Uh, if you send less number of samples during one period, okay, so you will get these type of fluctuations or these type of corners in the waveform. Okay, as you can see, we are just using 10 samples in one waveform, 10 or 12 samples or something. Okay, so we need to find the maximum resolution. So what is the maximum resolution? We need to determine the time period, okay, between one sample and the next sample. Okay, so we need to determine the time period between one sample and the next sample. So when we send the next sample, the previous sample has successfully transferred to the IC. Okay, so
Okay.
for that we need the IC and the oscilloscope operation. We need to determine uh, we need to determine the time period. So where is this time period is mentioned? So here, the function generator will have output rates. Okay, and we need to get at least 60% of the maximum determined. Okay, so let's suppose if the minimum time, and this time we will measure it with the help of oscilloscope. Let's suppose if the minimum time means minimum time to send one sample. Okay, so let's suppose if the minimum time is 50 microsecond. The maximum resolution is 20,000 samples per second. Okay, so basically if you divide 50 microsecond by 1 by 50 microsecond, you will get 20,000. So that means you will get 20,000 samples per second. So that is the actual resolution, but we need to stay within 60% of that resolution. So we need to send at least 12,000 samples in 1 second instead of 20,000. So we need to make sure that we don't overlap each sample. Okay, so this is the important thing, the minimum time. Okay, where is this mentioned minimum time? I think to precisely control the output DAC
Okay.
before
Okay,
calling the
okay. So I
register.
understand.
Yeah.
Okay. But can we work with the resolution and the spy communication later? Like, would we be able to work on the other stuff first? Um, like, would that be
Okay.
possible over the next couple of days, and then like by Saturday we can test?
Your classmate might have any IC, spare IC. Maybe they might have already. Can
I can
borrow.
ask, but I wouldn't. I'm not too sure. Sorry.
Okay, you can ask if you can find it for just 1 day or maybe 2 or 3 hours. So we can come and try to find out this timing, because this timing will determine the number of samples we have. Okay,
But can we
and
not change?
all.
Can we assign it like a? Can we assign it a value and then change it later?
Yeah, we can totally change it later, but for that you need to have a constant oscilloscope with you, because I need to check what timings you are getting.
Okay.
I can make the code, but yeah, later
That's okay.
on we
We
will need
can,
to change. Yeah.
that's fine. Would you be possible to make it and then we can spend a day or two testing it, like with the IC later on, and then we can change values as needed?
Okay. So can you tell me what date exactly is it due? Uh,
Uh,
5 days from now.
the first.
First. Yeah. Okay. Yeah. We can get it done, but if you can get hold of the IC maybe
Sure.
from your classmate, then it will be super awesome
Okay.
and easy. Okay, so let's continue with our previous lab. You have
Yeah.
any
Can we
questions?
go over eight? Yeah. I wanted to go over eight if possible. Like maybe you can share the code from your screen and then we can go over like line by line in the registers you did. Kind of how we did in the very beginning with like A4. Like maybe we can do
Okay.
it with A8 and just go over in detail.
Okay, so I can explain that, but do you have any questions, like you have any confusion regarding the communication? Did you able to get the screenshot on the oscilloscope?
Oh, we weren't able to get lab access, so the instructor told us not to worry about that.
Oh, I
Yeah.
see.
So I just took a video of the like light turning on, like once the code was running, if that makes sense.
Okay.
But yeah, I understood what to look for in the screenshot, but like we weren't able to do that. So it's fine.
Oh, I see.
Yeah.
Okay, I can share my screen.
Okay.
You can stop sharing yours.
Yeah. But yeah, so if we can go over kind of like the code itself, that would be good.
Okay. Let me open some files. Give me a second.
Yeah, sure.
Okay, you can see my screen. Can you see now my screen?
Yeah.
Okay, so we are using I2C communication. Okay, so there are around three modules in your nuclear board. So I2C1, I2C2, and I2C3. But we are using only I2C1 to communicate with our what was the name of the IC?
The
Yeah,
EEPROM.
20, yeah, the EEPROM 24LC256.
Yeah,
Okay.
yeah, yeah.
So, so in order to check what pins can communicate with the EEPROM, we can use the data sheet. Okay, so you go into data sheet and you go into pinouts and description. And if you go into alternate function table 17 and table 18, okay, so you will get it in table 17. You can look for, so this is for timer, these for timer 1, these are timer 2, this is I2C1 table, and I2C and I2C3. Okay,
So
so
what are you? So you're configuring a specific register to AF4, the alternate function register to AF4?
yes.
Okay.
So right now the port A does not support AF4. Okay, so if you go into below, so you will see the port
Okay.
B. So port B has many pins which can be used with AF4 functionality. Okay, so
Okay.
I am using PB9 and PB8 for the AF4 for the I2C one communication, and we are
Understood.
using two lines. One
Yeah,
is the
the clock
SCL
line and the
and one
data
is,
line.
yeah,
Yeah.
serial data line. Okay, so we have AF4. So if we go into the code, this is the code I sent to you. Okay.
Yeah.
So first we enable the clock for port B, okay, with the AHB2 ENR register. So we
Sure,
first
sure.
enable the clock, then we go into register mod register. Okay, so basically we define the mod. Okay, so first mod is 0 0 0 means input, 0 1 means output, and 1 0 means alternate functionality AF. Okay, and fourth mode is
So we
analog,
have to
but
set
we are
it
using,
to uh
yeah,
10.
A0 10.
Yeah.
Okay, so we have two bits, and we need to set them 1 and 0. Okay, so as you can see, this is the mod value for pin 8. Okay, so mod 8 means first we are clearing it. Okay, so first we are resetting all the bits, and then we are giving one value to first bit to the second bit. Okay, so the first bit will be 8 underscore 0, so that will be first bit, and we need to keep it 0, so we will not write it. And the second bit, if I open this one, you will understand. So you see, so this is the whole mod 8, uh, like what do you call it, mask, we call it mask for
Yeah, so I
bits.
understand you're clearing it, right?
Yeah, we are clearing it, and this is the bits of bits, each bit of
Yeah,
mod.
but I don't understand. So you're clearing it, but then why are you setting it to 1 after?
Okay, so we clear things. Okay, so when you have large number of code, okay, like a large size of code, you don't know if that pin is already being used by some
No, I
other
understand
functional.
why you clear it. I'm saying why do you put it as a 1 1? It looks like it's set to 1 1 instead of 1 0.
Okay, so this is for pin 8 and this is for pin 9. I have joined them combine like as a combined operation. Okay,
Right.
otherwise you can do it like this.
No, no, no. Okay.
Yeah. So
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 you want to
basically
set, so you're setting, so you're
yeah,
combining pin 8 and pin 9. You're setting,
yeah,
but don't you want both of them to be 1 0?
yeah, they are
Oh, I
one
see,
zero
I
right
see.
now.
So the underscore one means 1 0, right?
Yeah,
I thought it
underscore
was
one means,
wait, can you
so
hover
this
over it? I
is
just want to see
first
the
bit.
number. I just
Yeah,
want to see the number. Like,
yeah.
what's the macro for it?
If I go,
No, no, not that,
yeah,
not that, not
if
that.
I,
Go back to the code. Go back to the code. Just hover over. I just want to see the number that's being. Okay, okay. Yeah, so it's
yeah,
a one
yeah.
zero, not a 1 1. I thought underscore one was 1 1. That was my question.
Yeah, yeah. Okay, so basically this is the complete mask of 2 bits. Okay, we clear that
I'm
mask
following now.
and
I'm
then we,
following now.
yeah, and we use this underscore zero and underscore
Score
ones
one to do
for
zero, one
the
and one zero.
underscore zero means first bit and underscore one means second bit. Okay,
Okay,
and since we need to set one
both.
zero, so first bit will remain zero. We need to set this second bit. Okay, so that's why I am setting this
Do you want to
second
set
bit.
you want to set both 8 and 9? One is, so 8 is the clock, 9 is the um so 8 is the clock,
Yeah,
that's PB8, and 9 is the
yeah,
data line PB9, and you want to set both of them as alternate function 4, which is what you're doing. Well, you're setting it to
yeah. So
alternate function
basically,
first.
alternate function first.
Yeah.
Now we need to decide what alternate function we need to choose. So we need to choose AF4. So AF4 means if you AF4, so 4 means
I do
100.
see.
No, no,
Yeah.
no. Yeah, I to C, yeah,
Yeah.
AF4. So we go into AF. So we have two register of AFR. So one is the low register and second
Right.
is the high register.
Depending
Do
on
you
the
want me to
value.
show it
No.
again?
No. It's
Yeah,
okay.
depending on the
I understand. So
GPIO
the
pin.
AF, the second
Okay.
register, like AFR2, that's going to be higher numbers, right?
Yeah. So AFR zero register, lower register, is for pins from 0 to 7. But since we are dealing with pin 8 and 9, that's why
Understood.
we are using the higher register.
Understood. Is
Okay,
there a
the
two?
second
Is
register.
there another one like AFR2? Just curious. No, right?
Yeah,
Oh, there is?
yeah, yeah. Let me quickly show it to you. So if you go to GPIO, go to registers and go to AF. So this is the alternate function. Uh, Registers. Okay, as you can see, so this is GPIO AFR. L means lower. Okay, but in coding, um, we as you can see, so this is AFSL0. 0 means for 0 GPIO, and this is AFSL1. So maximum is AFSL number 7. Okay,
Okay.
so this lower register is for GPIOs from 0 to 7 maximum. Okay, because the maximum number of bits are 32. Okay, and each AFSL has 4 bits. So total number of 8 GPIOs multiplied by 4 makes it 32-bit register. Okay, and if you go into AFR, H means higher register. Okay, and you can see it starts from AFSL number 8. Okay, and this is AFSL number 9. Okay, and each one has 4 bits, like from 0 to 3. So pin GPIO PB8 has 4 bits and PB9 also has 4 bits. Okay, and we need to choose operation AF4 on all 4 bits. Okay, so it will behave similarly like the mod register. Okay, so we will select the AFRH. Okay, and we will select AFSL8 for the PB8. Similarly, AFSL9 for PB9. So first we clearing all the mask bits, okay, and then we are enabling only the relevant bit. Okay, as you see, we need to enable 0, 1, and 2 means second bit. Okay, so that is why I am using this AFSL8 underscore 2. That means this is the uh, second bit if we start from 0. Okay, and this is the second bit for the pin number 9. Okay, and if I quickly show you, open the declaration, so you see, so this is the AFSL8, so this is the complete mask, and these are the 4 bits inside the each mask. Okay, and we are enabling only this bit, pin number 2. Okay, you have any question till here?
No.
Okay, then we are just enabling this speed. Okay, since
So just to
we are using
confirm, the
maximum speed.
AFSL8 underscore 2, that's a 4, right? 100.
Yeah, 100. Yeah,
Okay.
because the AFSL 8 underscore 0 and underscore 1, they are already 0 here. I have
I know.
made
Okay. I'm
sure.
following. I'm following. Yeah, yeah. Okay. And then the speed you
Okay.
set to high speed. I'm familiar with that.
Yeah,
What does
highest
open
speed.
drain mean? Like, what
Um,
does that mean as a concept for the PUPDR? What does open drain mean?
Okay, so open drain is a functionality where we tell microprocessor to not attach anything to the um, MOSFET driver. So that is a just higher concept issue. So basically, when we make a push-pull configuration, so if you have a pin like this,
Oh,
okay,
that
you
means you're not
have two
pulling it or
MOSFET.
you're not pushing or pulling it to a
Yeah, yeah, we are not pushing and pulling. So basically, we have two transistor. So one is the NPN and one may be PNP. Okay, so
right, right.
we make it high or low. Okay, so
Yeah.
open drain configuration is simply like this. So you make it ground. Okay, and this is the pin. Okay, and you open its collector, so it's called open collector configuration. Okay, and you
Okay.
can attach like pull up resistor. Remember we attach pull up resistor
Yeah.
to
On the
3.3
board.
volts. Okay,
Yeah.
so we can externally attach pull up resistors.
Okay.
So this is external part, so that is the open drain. So this is a drain in the MOSFET, and
I have
it
a
is
question.
collector. Yeah,
Why
yeah,
are we using an external pull-up resistor instead of the internal one?
because we cannot set one. Yeah, we can totally set it. Okay, so we can totally set it inside the code, but the internal resistor of the nuclear board, they are fixed already. I think they are fixed at 47 kilohertz, kilo ohm, 47 kilo ohm maybe.
Oh, okay.
So those are high values. Okay, they will not operate for us. We need to have less than 10 kilo ohm resistor. Okay, if we have high resistance, the clock will stretch itself. So when the clock turns on, instead of going like this, the clock goes like this. Okay, the more resistance that we have, the more time current will take from going 0 to high value. Okay, because it faces a lot high resistance now. So that's why we use external pull-up resistor. And most of the ICs which operate on I2C, they already have pull-up resistance. Okay, so we tend to disable the push-pull configuration inside the microcontroller. Okay, we
Okay.
do not open it. Yeah, so we keep the drain or collector open, so we can attach the external pull-up resistance. Okay, So that is the push-pull configuration. So we are disabling the push-pull configuration and we are keeping the open drain configuration with the help of ODR register, open drain register. Okay. So we are enabling the we are enabling the only bit, which is for the number 8 and number 9. Okay. So that is the GPIO configuration till here. Now, uh, three or four things we need to keep in mind. Okay, so first is the
What is a
address
own
of
address?
the.
What does that mean?
Okay, so this I2C device can work as a slave as well, and and as a master as well. So your nuclear board can also act as a slave. Okay, so when it will act as a slave, it needs to have its own address. Okay, so the
Oh, okay.
master
I
can
understand. Because it was like,
initiate.
remember the
Yeah,
address was like 50 to 57, something like that, right?
yeah.
Okay.
Yeah. Okay. So you can write any address. So it gives you like A3. Okay. So you can choose a 7-bit address. Okay. For your own microcontroller. So there is a register. You can use that. Okay. To set the address of the nuclear board if you want to use it as a slave device. Okay. But since we are dealing with a master device, we are not concerned with it. But since in order to make the configuration proper, I just put it here. Okay.
Understood. Okay.
Yeah. Okay, so the first step, first is the foremost step is, first we need to enable the clock for I2C1. Okay, first we enable the clock. Okay, and then we select the clock source. So you don't concern with it. So let's just leave it, because we are using the same clock for each peripheral. Okay, and this is the register APB1 RSTR. So basically this is a reset peripheral register. Okay, so basically let's suppose if you have previously used I2C communication for let's suppose you have two I2C based I2C based modules. Okay, and if you have used a different configuration for a separate module, and you want to use the EEPROM now, you may want to reset all the previous registers. Okay, so basically that bit is going to reset all the registers of the I2C all at once, instead of going one by one each. Okay, so basically we reset the I2C communication and then we unreset it. Basically first we disable it. Okay, disable the power, all the registers go zero again, and then we enable the I2C communication again. So just don't, so this is just for resetting. This is not concerned most of the time
Wait,
if you
scroll
have
up a
only
little
one
bit.
module.
Scroll up a little bit.
Yeah,
Okay. So the after initializing the clock, you're just resetting
yeah,
a lot of registers.
yeah, yeah. I am
So like the first one is like you're setting the CCIPR, the two lines above.
yeah. So if
So
I
what is,
may
wait,
show
so
you,
first of all, RCC, is that a register?
yeah, RCC is a recent and clock control register.
And what is
Okay,
CCIP?
CCIP means it says
Oh, that's a more specific
uh,
like peripheral clock.
yeah. So CCI means clock control
It's like
independent peripheral register.
APB like when we use APB for like GPIO or whatever, right? Or
Let me quickly show you. First, let me rename it. Otherwise, it will not open. Program A. Okay. If I open this one, and if you go into clock, so basically each peripheral has multiple clock options. Okay, you can choose any clock option. You can choose it to run directly from the crystal oscillator. You can choose it to run from the system clock. You can choose it to run from the peripheral clock. Okay, so basically you have two type of buses. One is the APP bus, one is the AHB bus. Okay, if we go into clock configuration, and let me show you where is the I2C one. Okay, I think it's here. Yeah. So as you can see, so this is I2C clock mux one. Okay, so you can take the clock from peripheral clock PCLK, which is the APB bus. Okay, or you can take the system clock, which is the AHB bus. Okay, or you can use directly the HSI. HSI means 16 megahertz high speed internal clock. Okay, so you can use any of these clock based on your setting. Okay,
Okay.
and if you go above here, so you will see different clocks. So this is HCLK, which is the AHB bus, AHB clock, and this is the APB1 peripheral clock, APB timer clock, APB2 clock, APB2 timer clock. Okay, so different modules or different peripherals of the nuclear board are connected to different clock speed. Okay, and you can reduce clock speed with the help of prescaler as well. Okay, as you can see, this is, if you see my mouse, so the actual clock is the AHB clock. Okay, uh, from here. So system clock is the AHB clock. And if you put some prescaler, you can divide the clock. Okay, you see the clock is divided by two. So it becomes so it becomes 2 megahertz now. So basically, you can choose any clock option available. Okay, so that register is doing that. Okay, so now we go to the actual I2C communication. Okay, so in order to if we go into CR1 register quickly, I2C is 39. If you go into registers, and this is the first register, I2C is CR1, control register 1. Okay, so it has lot of these bits. Okay, we need to select um, which ones we are concerned only. Okay, so this is
Also,
the
just
first bit
FYI,
is
we're
the
gonna run out of just we're gonna need to start a new meeting soon. Just letting you know.
okay, okay. So
Yeah.
first bit is the peripheral enable bit.
Okay.
Okay, so it
So go
says
back to the code,
when
please.
yeah.
Okay.
So we are using I2C CR1. Okay, and first we are disabling the so first bit was the
Okay.
looking at it.
Yeah, if you can go back and forth, that would help too.
Okay, so you says when PE is 0, I2C I2CL. So basically, you need to make the PE0 bit to 0 in order to configure the stuff for the I2C. Okay, so
Understood.
first we are disabling.
Yeah.
First we are disabling it. Okay, and then we are enabling the analog and digital filters. Basically, we are not
So
using digital
really,
filter. We are using only analog filters.
okay. Okay.
Yeah.